Okay, and when you try to put them together, you can see that the red ball is coming over the red, the black ball is coming over the black. Okay, but the green and blue balls are not matching. Okay, so this is what happens when there is a chiral carbon. If there is a chiral carbon, it is a carbon which is connected to 4 different groups. Okay, in our question they were methyl, ethyl, hydrogen and bromine. But in order to show you, in order to explain you what we did, we have covered, we have put balls of 4 different colors, black, to indicate that there are 4 different groups. Okay, and I have made 2 isomers having these same 4 different groups. Okay, but they are actually mirror images of one another, right? They are mirror images. This dotted line is actually a mirror image. Okay, you can see, you can imagine if you bring the molecule A near to the mirror, you will have a mirror image of A, which is B. Okay, in which the molecule will look exactly same. But let me tell you, if it is a chiral carbon which is connected to 4 different groups, then the mirror image is actually non-superimposable on the original molecule, means it is different from the original molecule, and hence this is not, this 2-bromobutane is not one isomer, single isomer, but they are 2 isomers. Okay, these are known as stereoisomers, right? Is it clear to you?
Yes, sir.
Okay, they are non-superimposable on its mirror image. They are also known as enantiomers. Stereoisomers, what is the difference between stereoisomers and structural isomers? Tell me. Yeah. What is the difference between structural isomers and stereoisomers? Yeah, Krishna. Structural isomers, it is very easy to see. They will have different connections. Okay, like 1-bromobutane and 2-bromobutane were structural isomers. Okay, if you compare them bond by bond, they will have different types of bond. In 1-bromobutane, the bromine was connected to 1 position. In 2-bromobutane, the bromine was connected to 2 position. Okay, they were having different connection, different types of bond. In 2-bromobutane, the bromine was in the middle, while in 1-bromobutane, it was at the end or in the beginning. Okay, so those were stereoisomers. Okay, so sorry, those were structural isomers, positional isomers. Okay, so first you need to write the positional isomers or the structural isomers. Then you need to check that where the chiral carbon is forming. You need to check each and every carbon in the product. Okay, you should not the carbon chain the way which you did. Okay, by putting methyl at the carbon atom which is connected to Br, you should not change the alkyl group. Okay, alkyl group should remain same. You put the bromine at different position and find out what how many new positions at how many new position the bromine can come, right? And then you need to check. So those with that you get all the structural isomers. Okay, positional isomers. Okay, because bromine have different position in all those isomers. Then you check actually each and every positional isomer, that where the Br, or is there a chiral carbon atom being created after the attachment of bromine. If it is created, you consider that the molecule bearing the chiral carbon not a single molecule, but actually you consider it as 2 molecules. The molecule itself, the molecule itself has 1 isomer, and its mirror image isomer, which is the second isomer. Okay, the mirror image isomer may look exactly same as that of the original molecule, but actually because it is a chiral carbon, it is 4 different groups. The mirror image isomer is not same. It is different. And how you are going to satisfy yourself that it is different? You need to superimpose them on one another, and then you will realize that these 2 molecules are not same. They are non-superimposable mirror image isomers. So for chiral carbon, there are 2, isomers. Okay, and these two mirror image isomers are known as enantiomers, right? Is it clear?
Yes, sir.
And not only the carbon can be chiral in our day-to-day life, there are other things also which can be chiral. Okay, for example, normal specs, chiral means chiral is a geometric property. It can the molecules can be chiral, okay, or it can be found out in our day-to-day life objects also. For example, if you have spectacles, right? They are achiral, means they are superimposable on it on their mirror image. So if you make a mirror image out of a glasses, okay, you will have the same glass, right? And
Yes, sir.
if you try to bring them on one another, they will overlap very easily. So it means they are superimposed. They are not two objects. This is only one type of object. Okay, achiral is superimposable on its mirror image. Means it is only one. Okay. Suppose if you have a glass which is like this one. Okay. Where do we have this kind of glasses? Have you seen anywhere?
So polarizing glasses or something?
The
No, sir.
polarizing glasses, and sometimes we
3D
have that.
glasses.
Yeah, 3D glasses. They have some blue and green. Okay. Yeah. The 3D glasses maybe like this. Okay. So if you draw the mirror image, so in this one, the right lens is blue colored. Okay. And in that the left lens, in the mirror image, it is a left lens which is blue color. So if you try to bring them together, they will not superimpose. Okay. Right? So it is a chiral thing. It is a chiral object. This property can be assigned to objects also. This property can be assigned to molecules also. The definition of chirality is non-superimposability of mirror images. Is it clear? So the molecule need to have a chiral carbon atom, then only it will be chiral. Okay, it will have 4 different groups. The carbon will be connected to 4 different groups. Okay, and if it has 4 different groups, if you make a mirror image of that molecule and the mirror image will be different. You need to superimpose and know that they are different. Okay, and then you know, okay, if we are getting some by attachment of bromine at different position. Suppose if a chiral molecule is being created, okay, then you need to consider that molecule as 2. Okay, because that chiral molecule will be of 2 types, the molecule one itself and its mirror image. Is it clear? So you can see that they are not identical, and I have tried to create a mirror image, and then I have tried to superimpose, and you can make out that they are different. Is it clear? There are other things also which are different. The word chirality has come from hand. Okay, because hand is chiral. How can you explain me that the hand is chiral, Vamsi? Tell me.
So they are non-superimposable mirror images. Like when we place palm on palm, we find that they are not the same and like
Yeah,
they are not symmetric.
yeah, yeah. So people say that this is superimposition. Okay, this is not superimposition. Okay, you need to bring one hand into another. Okay, then you will realize. Or superimposition is actually if you can't wear your right hand glove in left hand. That glove superimposes. So both the hands are different. Okay. So it is hand is chiral, and the word chirality has come from that handedness or hand. Okay, it has come from. It is a geometric property. It can be given to normal day-to-day life objects. Also. Our shoe is chiral. If you take a shoe of right leg and try to make its mirror image, it will be the shoe which will belong to the left leg. Okay, so it is a chiral.
So
Here
how is
is
the
chiral.
screw, Kyle?
Screw actually is having that threads. Okay, and the threads are not actually horizontal rings. They are going in a slant way. Okay, like this. So you have right-handed screw, and if you try to draw a mirror image, it will be left-handed. So one, you need to, if you need to tighten that one screw, you need to rotate it clockwise. The another one, the mirror image, you need to rotate it anti-clockwise. Then it will get tightened. Okay. Is it clear?
Yes.
So they are actually non-superimposable. You need to look at threads because of the unsymmetry in threads. But there are many things which are symmetrical and which are chiral, which do not have two different forms, because the original thing and just a second, and the original thing and the molecule, there is a part. The original thing and the molecule both are actually superimposable on one another. Okay. Is it clear?
Yes.
Right? So just a second. Yeah, I hope you can hear me.
Yes, sir.
Yeah, so a fork is actually achiral because it is symmetrical. Okay, a normal table is achiral object, it is symmetrical, and if you try to make a mirror image, it will be superimposable on itself. Okay. So normal things can also be chiral or achiral. If they are chiral, they are non-superimposable on their mirror image. Is it clear?
Yes, sir.
And if the molecules are chiral, then they are non-superimposable on their mirror image. Same thing is applicable to molecules also. Then you should and how you know that the molecule is chiral?
Sir, it is attached to 4 different groups, right?
Yeah, it will be attached to 4 different groups. Yeah, then only it will be chiral. Good. And if a molecule is chiral, because all these things which are chiral, which I have shown you, have 4 different sides. Okay. So this side is different, this side is different. Okay. All the sides are different. It is different from different sides. That's why it is chiral. Okay. So suppose if you have a molecule which is connected to 4, or a carbon atom which is connected to 4 different groups, then it is a chiral. Right?
Yes, sir.
Clear? So chiral molecule is having a non-superimposable mirror image, and you need to consider them as 2 molecules. Okay. So here you can see a chiral molecule. Okay, we talked about 1 bromobutane. So total how many isomers? 3 isomers. Okay. Yes, you understood how 3?
Sir, enantiomers are the synonyms of chirality, right?
Enantiomers are actually, yeah, enantiomers actually that the chiral molecule and its mirror image. Okay, the chiral molecule and its mirror image, they are actually known as enantiomers. Enantiomers are, the definition of enantiomer is non-superimposable mirror image isomers. Okay.
Okay.
Yeah, so there are 3 total. If someone asks you, you need to. So if someone say that draw the structural isomer, you will not go into deep. Just you will put Br at the first position or at Br at the second position. Okay, that's it. Two structural isomer. But if someone asks you, draw the structural isomer, draw the stereoisomers. Okay, total isomers. Tell me the total isomers. Okay. Then you need to answer, then you need to say that there are three molecules. Okay, why, how come 3 molecules? Okay, how come 3 molecules? Because the 2-bromobutane is having a chiral carbon atom. So the molecule 2-bromobutane and its mirror image Okay, because it is a chiral, so its mirror image is going to be different. They will be different, right? And they will be known as enantiomers. Okay, clear?
Yes, sir.
So it will be different, right? So that's you need to consider. And so a chiral molecule, if suppose any two groups are different, then it is not a chiral carbon. Okay, so someone may say it may also will have a mirror image. Okay, so its mirror image I have drawn. C and D are both mirror images, but they are same. They are not different from one another. Okay, just flip it like this. You can see over here. So now the black balls both come on the left hand side. One is at the top, one is on the left hand side. So I've rotated C to make it to try in a. So I want to try to check whether the C or D are different or not. Okay, so C I rotated it. Okay, the two black balls, one is at the top, another is on the left hand side. Okay, and this blue ball will go inside and the green ball will come like this. Okay, it will become like this. Okay, the blue at the, okay, clear? Or you can check that they are superimposed. Is that clear?
Yes.
So they are superimposable, so you don't have, if there is no chiral carbon in the normal molecule, you don't have to think of two different molecules. They are same. Okay, is it clear?
Yes.
But if you have a chiral carbon, then which is all four, in which all four different groups are different, then you need to think. Then you need to think that there are two different molecules having same four different groups, but they have different 3D elements which are mirror images of one another, and these two mirror images non-superimposable mirror images. Okay, they are known as enantiomers. Okay, so enantiomers are non-superimposable mirror images of a chiral molecule. Clear?
Yes, sir.
Right? Okay, good. Other thing is, what is the other property of chiral molecules? Tell me. What is the other property? One property is that they were non-superimposable on their mirror images. Okay, they were two different, though they looked same, but they were two different forms which were not superimposable because they were different. That's why they were not superimposable. Okay, the other, and they were called as enantiomers, right?
Yes.
And which other property? Which other property is there for chiral molecules? Okay, can you see here? What does this mean?
Optical activity.
Optical activity. Yeah. So what it means? Tell me. What optical activity means? Yeah.
So it changes the plane of polarization of light.
Yeah, exactly. So optical activity is a phenomena of rotation of plane of polarization of light. Okay. So suppose if you have a chiral molecule in which there are two different non-superimposable mirror images, because the chiral carbon is the carbon which is connected to four different groups, and because it is connected to four different groups, all the four groups are different and its mirror image is not superimposable on the original molecule. Okay. Clear?
Yes, sir.
So they are non-superimposable on one another. The other property which is different for both of them is they both exhibit optical activity, right? Optical activity is a phenomena. Chiral molecules are optically active. So you have a plain polarized light. Okay, this whole setup, you don't have to do it separately one by one on your own. Actually, it is there in a lab. This is instrument. All of these which I've shown you is the part of your instrument, which is known as polarimeter. Okay, clear? So
Yes, sir.
this whole instrument is known as polarimeter. Okay, so polarimeter has a light source, and the normal light is which is coming out. The light is electromagnetic wave in which the electric and magnetic field are oscillating. Okay, so these two double-headed arrow are showing the oscillations of the electric and magnetic field. You can see, and they are in all the directions. Means if the light is coming towards you, the oscillation of electric and magnetic field is like this or like this, like this. Okay, it is in all the direction. This is known as non-polarized light, normal light, non-polarized light. Okay, and there is a polarizer filter. Okay, a polarizer filter, this light that is the part of that polarimeter itself. Okay, you don't have to bring the polarizer filter externally. Okay, so the normal light is passed through that polarizer filter, and it has a crystals aligned in a specific manner. So it is just like a slit, and it will let only one light, one type of light having one plane of polarization pass through it. Okay, so after the light, the non-polarized light after passing through the polarizer filter get filtered out, and you have a only one type of light in which the polarization is there is a the electric and magnetic fields are oscillating in only one direction. Okay, one plane, and this is known as plane of polarized light, PPL. Okay, clear? Any doubts?
No, sir.
And this, and there is a tube. This tube is removable. Okay, this tube you can see. You can, and there are glasses on both the ends. On this end and this end, it has glasses. You can fill your compound in it. Okay, and that polarized light enter from one side through the glass. Okay, you put that compound for which you need to check, for which you want to check the whether it is optically active or not. Okay, you make a solution out of it and you fill this tube. The polarized light pass through this tube. Okay, and if the polarized light rotates, okay, you can see over here, then the molecule is considered to be optically active molecule or a chiral molecule. Okay, is it clear? So this is the chiral molecules are optically active. Optical activity is a phenomena of rotation of plane of polarized light. Okay, chiral molecule rotate the plane of polarized light. Chiral molecule are non-superimposable on their mirror image. That's what the word chiral means. Okay, so and the two mirror image, the two molecules thus resulted by forming a mirror image. The molecule, original molecule and its mirror, both are non-superimposable, and both are chiral. Okay, and they are known as enantiomers. Okay, they are mirror images. Okay, they have same type of bond. They have same type of group, but only the 3D arrangement of group is different. In one, they are arranged in clockwise manner. In another, they are arranged in anti-clockwise manner. Okay, that's why they are not able to superimpose on one another. And if you put these two molecules in polarimeter separately, okay, these two molecules are known as enantiomer. You will find that the one molecule, if it rotates the light in clockwise direction, the other molecule, which is the mirror image of the first molecule, will rotate the light in anti-clockwise direction. Rotate the plane polarized light in anti-clockwise direction. Is it clear?
Yes, sir.
Okay. But a chiral molecule is symmetrical. Do not have a different kind of mirror image for a chiral molecule because it's the molecule and its mirror image are both same, superimposable, and because it is symmetrical, not all four groups are different. If you pass the polarized light through it, it will not rotate in any direction. So you can see over here. Where? So
Yes, sir.
the lower molecule is your lower molecule is the case of a chiral molecule or optically inactive molecule. The upper case is of chiral molecule or optically active molecule. So chiral molecules are optically active. They rotate the plane of polarized light. Okay, and the chiral molecule will have non-superimposable mirror image, and they are known as enantiomers. One enantiomer, if it rotates the light in clockwise direction, the other one will rotate the light in anti-clockwise direction. Okay, is it clear?
Yes, sir.
But only chiral molecules will do this. Okay, and that is a property which is different among the two enantiomers, right? So here you can see chirality and optically active. Compound that rotate the plane of polarized light of polarization are said to be optically active molecule. Chiral molecules, chiral compounds are optically active. Achiral compounds are optically inactive. They do not rotate. Okay, chiral molecules have two different mirror image. Are of two types: the molecule itself and the mirror image. So one will rotate the light in the clockwise direction. Okay, another will rotate the light in the anti-clockwise direction. The one who rotate the light, and you need to have that polarimeter set up to tell whether the molecule is rotating, whether it is optically active, whether it is not optically active. Okay, just by looking at the molecule, you can't directly say whether it will rotate or not. Okay, so you need to check experimentally. Okay, but if there is a chiral carbon, you can tell directly. Okay, it is going to be a chiral molecule. It will rotate plane of polarized light. But whether it will rotate in clockwise direction or anti-clockwise direction, that you need to check with the help of polarimeter. Okay. So the molecule, optically active molecule, which rotate the light in the clockwise direction is known as dextrorotatory molecule. Okay. It is also represented by D. It is also represented by plus. But there is also in organic chemistry, there is a letter capital D. Okay. Is it clear? Yeah. But capital D actually, okay, is a different thing. Okay, we will discuss it in biomolecules, right? As of now, you should some optically active molecule which rotate the light in clockwise direction is dextrorotatory. It is represented by small d or positive sign, but not by capital D. That has different meaning. We will discuss it in biomolecules. Okay, is it clear? A molecule, so one isomer will rotate the light in clockwise direction, PPL. Its other isomer will rotate the light in anti-clockwise direction. Okay, that will be known as levorotatory, small l. Okay, or minus sign. It is indicated by minus sign. Okay, so you take two mirror images, but that facility is there only for your optically active or chiral molecule. Right? Clear? So here is an example of a chiral molecule. You can see, not the one which is generated by bromination, but that too bromobutane also you can have this kind of setup, this kind of representation. And this is 2-methyl butane, 1-butanol. Okay, there is a plus sign written before its name. Okay, what it means?
It's a clockwise direction.
It is a optically active molecule. Okay, but it is optically active that you can tell orally without checking. Okay, because it has a chiral carbon. This is a chiral carbon. Okay, you can see that this carbon is connected to CH2OH, CH3, CH2, CH3, which is ethyl, and hydrogen. 4 different groups. This is a chiral carbon. This will be optically active. That you can tell, but you will not be able to tell whether it will rotate clockwise or its mirror image one is going to rotate the light in the clockwise or anti-clockwise direction. For that, you need polarimeter. Okay, so this is the mirror image. Mirror image you can create, okay, in this way. In optics also we do mirror image. Okay, so when you draw a mirror image, you will see that these two molecules are there and they are non-superimposable mirror image, but you need to put each and every molecule individually, one type of molecule into polarimeter and check whether it rotates clockwise or anti-clockwise. And this one is rotating, let's say this is found by experiment in clockwise direction, this is dextrorotatory, and that's why the plus sign is there. So if you find out that one of the molecule is clockwise, then its other mirror image isomer, that you can say orally that it will be anti-clockwise. But at least one of the enantiomer you need to check through with the help of polarimeter. Okay, just by looking at the structure you can't tell. Is it clear? And
Yes, sir.
this is the value of rotation. So that plane of polarization which is coming like this, okay, once it has passed through this molecule, once it is filled into that polarimeter tube, the plane of polarization will rotate by clockwise, okay, clockwise by 5.75 degrees. And this is the temperature. This is known as specific rotation. Then this is the temperature of 20 degree, and this is the wavelength of sodium light, which is represented by capital T. Okay, but this doesn't matter. Okay. So if you take another compound separately in a polarimeter, and check its optical rotation, the another compound is a mirror image of the original compound, then it will have a rotation of negative. Same by same magnitude, okay, but in opposite direction, anti-clockwise. This is levorotatory and this is dextrorotatory. Is that clear?
Yes, sir.
So this is when they are taken separately. Okay, dextro you have kept separately, levo you have kept separately. Okay, you have check their rotation, optical rotation individually. Okay, in polarimeters, different polarimeters. But what happens? So these two are. So what is the relationship between a dextrorotatory compound and the levorotatory compound? Are the same molecule. They are mirror image isomers. Okay, is it clear?
Yes, sir.
But what will happen if you put them together? If you mix them together, what you will get? Yeah. What you will get?
So we'll get a racemic mixture.
Racemic mixture, yeah. Racemic mixture is equimolar mixture of two enantiomers. But that racemic mixture you can get only. So who will form a racemic mixture? One bromobutane or two bromobutane?
So 2 bromobutane.
Yeah, two bromobutane, because one bromobutane was achiral and it was having a same mirror image. Okay, it was symmetrical, so it was not having two different from dextro and levo. A molecule which is chiral, which has a chiral carbon, that can have two different forms. One is dextro, another is levo. And if you mix the two forms together in 50-50 ratio, okay, that is known as racemic mixture or racemate. Okay, and if you put them simultaneously in one polarimeter in equal amount, that is very important. Then only it will be considered as racemic mixture. And if you pass that light, if you pass that light through it, polarized light, plain polarized light, what will happen? What you can say about the optical activity of the racemic mixture?
So it is optically inactive.
Yeah, it is optically inactive due to external compensation. What it means, external compensation? Yeah. What it means? I have underlined it. You can see. Yeah.
So physical properties.
Yeah, external compensation actually is, suppose if you have dextro, levo, you have mixed them together. So the molecule, when the plain polarized light hits a dextro molecule, it will get rotated slightly in clockwise direction. Okay, when it hit levo molecule, it will be rotated in anti-clockwise direction. But because you have put both of them together in same amount, 50-50 ratio, overall there will be no rotation of light will be observed, though the individual molecule will be rotating at the light, but there is a net cancellation because you have equal number of dextrorotatory molecules and levorotatory molecule present in the same polarimeter tube. Is it clear?
Yes, sir.
So the in the path of the light, you will have polarized light will encounter same number of dextro and same number of levo molecule if you have put a racemic mixture, and that's why suppose with dextro it will get rotated slightly in clockwise direction, levo it will get rotated in that anti-clockwise direction, but overall it will not rotate, it will pass through, because there is a net cancellation, external compensation by two different forms of the same molecule, like which are chiral, okay, which are mirror images, okay. So that's why it is optically inactive. Is it clear?
Yes, sir.
And that optical inactive, actually the molecule, each and every molecule, if you try to look at each and single molecule, that will be optically active, but overall the light is not getting rotated because it is getting cancelled by both the molecules. Both the molecules are present in the same tube. That's why it is called external compensation. Okay. So these two enantiomers are there for two bromobutyne, one is dextro, another is levo. Now tell me, so one rotate the light in clockwise direction, another rotate the light in anti-clockwise direction. So this is a physical property which is different for the two enantiomers. Okay, the way in which they interact with plane polarized light, one rotate clockwise, another rotate anti-clockwise. Okay, the other thing is, how can you suppose if someone makes a racemic mixture out of them, and in the above question also we were getting the racemic mixture for two bromobutane, they were present in the same reaction mixture. Okay, now tell me how you are going to separate them. What is the way to separate the two forms? Yeah.
So by chemical methods and chromatography.
Yeah, chemical method and chromatography, but you can't separate them by normal physical methods like boiling, melting, right? Because both
Yes.
enantiomers will be frozen together, both will melt together. Okay. Yeah. You need some special methods, chemical resolution. Okay. So this is lactic acid. Okay, very famous molecule which is present in milk curd. Okay. Saring of milk. So lactic acid is actually optically active. It is a chiral molecule. You can say that it is chiral, right?
Yes, sir.
Without the polarimeter, you can say, but you can't say whether which one is dextro and which one is levo. For that, you need polarimeter, right?
Yes, sir.
For that, you need polarimeter. So this is the one which is levo rotatory. You can see the minus sign after checking it in polarimeter. So one, if you know that is levo, another one will be dextro. Okay, this is dextro. Its mirror image is going to be dextro, right? So
Yes.
if they are present together, you need some special method, chemical method and chromatography to separate them. And this special methods, the separation of enantiomer is, there is a special name given by UPSC, that is resolution. Okay, clear?
Yes, sir.
So this is the thing which you need to understand. And now let's move to another way of preparation of alkyl halide. So we completed the preparation of alkyl halide by photohalogenation, in which you take halogen along with alkane, you give some light of appropriate frequency and wavelength so that the halogen breaks into radicals and the radical abstract edge and get attached to the hydrogens on that alkane. That is called photohalogenation. Okay, and we discussed all the aspects of photohalogenation till now. Okay, now there is another method which we are discussing for the preparation of alkyl halide. Okay, that is by addition on alkenes. Okay, so alkenes actually have a double bond, right? And you add HX, right, on these alkenes. Okay, is it clear?
Yes, sir.
So what this addition is known as, and this is addition reaction. First of all, let me tell you why it is addition. I hope that is clear to you.
Yes.
But it is what kind of addition is it? Is it electrophilic addition, nucleophilic addition, free radical addition?
It's a free radical addition.
Free radical or electrophilic? It can be, the answer can be electrophilic addition and the answer can be free radical. It depends what are the intermediates involved during the addition reaction. Right?
Yes, sir.
What are the intermediates involved during the addition reaction? Okay, we need to look into detail. Okay, simply if H6 is given, then it is electrophilic addition reaction. So what is the mechanism for this addition? Yeah, tell me. Mechanism means, you know what is mechanism?
Yes, sir.
Yeah, so this is actually just the equation. Okay, it is not telling you what is happening internally. So internal step by step way of writing the whole things. Okay, that is known as mechanism. Okay, so what is the mechanism of this reaction? Yeah, tell me. Just little bit idea you can give me. Then I will explain you in detail. How much you know, you can tell me. Don't worry about it. If you don't know, you don't have to worry. I will explain you everything. Yeah.
Sir, in HCl, no, no, in ethene the double bond will be, it will become single bond, and the CH2CH
Yeah.
will attack.
Actually, yeah, what happens is if you take HCl, the HCl is an acid. Normally, what happens is so it dissociate into H plus and Cl minus, right?
Yes, sir.
And if you have taken an alkene, this is a mechanism which will tell you how it is happening internally, how it is happening. And if you have taken an alkene, who will get attracted towards alkene and can, where is the possibility of reaction happening with alkene? Is it the H plus which you expect can react with alkene, or is it the Cl minus?
Cl minus.
Why Cl minus? Why not H plus? Yeah, or both.
So both can take place, depending upon the
Actually,
charge.
it depends upon the charge. You told a very important thing, and with that only we are going to decipher who is going to interact with alkene, and we'll take the reaction ahead. So alkene is actually having that pi electron. Okay. Is it clear?
Yes, sir.
So it is having a pi electron, which is loosely held, and it is not like a sigma bond, which is along the line joining the atom. It is above and below the line joining the atom. Okay. Yes.
Yes, sir.
So it is above and below, right? So this is the electron cloud, electron density. Now you tell me which one do you expect? Is it the H plus or Cl minus? Cl minus is already having electron density on
So
its
H plus.
H plus, because Cl minus will be repelled away. Okay, so H plus is an electron loving species. It is having a plus charge, so you can expect H plus to react with it and will take the reaction ahead. So that's why this type of addition is known as electrophilic addition reaction. It proceeds via addition of electron. Okay, so H plus will come and it will suppose this is a pi bond and H plus is coming from this side. It will take the electron. Okay, the electron density will, H plus will form a sigma bond and it will, so you will have a carbocation which is formed on an atom adjacent to the place where the H plus has connected itself. The pi electron density now has been taken by H plus. Okay. And what will happen with Cl? What will happen with this plus?
The Cl minus will attack the
Yeah,
Cl.
now Cl minus can attack. Now this is electrophile, and that one Cl minus is nuclear. So overall, it is an addition happening, but it is electrophilic addition reaction. Is it clear?
Yes, sir.
Okay. So same thing you can do for HBr. Okay. Right?
Yes, sir.
So you can put H and Br. Same thing you can do for HI also. You can connect H and I. This is Markovnikov addition. What do you mean by Markovnikov addition? Yeah. Till now, in these questions, which I have shown you on this page, right on this page, you don't have to think that the double bond is present between two carbon, but you don't have to think where you are going to put H and where you are going to put Cl. The reason is it is same from both the sides. Okay,
Symmetry.
symmetrical. So you just put H on one carbon and Cl or another carbon, halide minus on another carbon. That's it, and you get the answer. You don't have to think more than this. Okay, but in this case, there are two possibilities because it is an unsymmetrical alkene. Yeah. So if there is an unsymmetrical alkene, what's going to be the answer?
So it will obey Markovnikov's addition rule.
Yeah, Markovnikov addition rule. And what it says, what it is.
So the halogen will go to the carbon which has least number of hydrogens on it, and it is attached to the double bond.
Yeah, or H plus will attach itself to the carbon atom bearing more number of hydrogens. Okay, rich become more rich, become richer. Okay, rich gets richer. Okay, so H I'm going to put here, Cl I'm going to put. So this is just an outer way of saying, understanding it, right?
Yes.
Is it clear? It is just an outer way of saying. Okay. But actually, what is happening inside, why it is happening? So this is Markovnikov addition. Okay.
Yes, sir.
So actually, what is happening inside? Why it is happening? We can see that there are two hydrogen on the right carbon and there is no hydrogen on the left carbon. So we are going to put Cl minus there and the hydrogen on the right carbon because there are more number of hydrogen. This is Markovnikov addition. Okay. So electrophilic addition on alkene is Markovnikov addition. Or the spelling, you will find two different spelling. Markovnikov, V is there, or Markovnikov. Okay, it is same because it is a Russian name and there are two ways of pronouncing it. So, but what is the internal thing which is governing this? That you need to tell. Yeah.
So I didn't get you.
Actually, why it is happening? That you need to explain. We are able to see that there are two hydrogen. If you does the H plus can make out where the how the H plus makes out where it should get connected and where the Cl minus makes out that which onto which carbon it should get connected. Yeah. Markovnikov rule is just the external way of saying for us. It is for us that we can put H on the carbon bearing more hydrogens and Cl on the carbon bearing less hydrogens, right? But
Yes.
internally, how it is happening, why it is happening, what is the reason, internal reason, why it is happening, that you need to tell me.
So when the halogen is on the carbon which is having like less number of hydrogens, then it will be more stable.
Yeah, actually, yeah, don't think in terms of halogen because halogen come only after the climax gets over. Okay, though you are saying is correct, whatever you are saying is correct, but you need to change the way in which you are saying. Tell in terms of H plus because that is the first place, that is the first step of the reaction. Okay, because once the H plus get connected, then on the adjacent carbon you have plus charge, and then the Cl minus will automatically connect to that plus. Okay,
Yes.
so you don't actually say, though you are saying whatever you are saying is correct, but you should say it in terms of H plus. So the first thing is where the H plus will connect itself. That's the question. On to which double bond. In the unsymmetrical alkene, this is a question need to be answered. For symmetrical, you don't have to bother at all because both the carbon are same. You can connect H plus to any of the carbon. Okay. In this case, you need to think that whether should I connect H plus on this carbon or H plus on that carbon. That you need to think in this way or in that, right?
So it will be in the second way because the
This
carbon is
the
having
one and two.
yes in the
Yeah.
first one.
So first one, yeah. So if the H plus is coming from this side, this is the double bond, okay? Pi electron. It will come this side, and the plus will come on that carbon. But if the H plus is coming on this carbon, second, okay, the double bond will shift like this, okay, and the plus will be on this carbon. So you need to consider both the cases. So this is the first way of attaching, and this is the second way of attaching. So first way of attaching will you by going through the route number 1, you will have H plus connected to CH2 and you will have CH3 and the carbon positive charge will be created in the middle. And then Cl minus will get attached itself to that middle carbon. Okay. But if you attach H plus on the left second method, okay, then you have positive charge on the right hand side. And that is not the favorable way of doing the reaction. That will not lead to the Markovnikov product. So what is actually governing the whether you should adopt route number 1 or route number 2? Yeah, what you were telling?
So the substance attached to the main carbon, which is bulky,
Yeah,
avoids the hydrogen going to that carbon
yeah.
instead of.
Actually, no, not the bulky. Actually, suppose if the carbocation, actually the H plus should connect in a way such that the plus charge come on more branched carbon atom. Okay, more substituted carbocation, because these alkyl groups are not electronegative and they are electron donating. They push the electron slightly, okay, towards the plus, and that makes plus stable. Okay, clear? So plus charge, it is the actual governing factor is the stability of the plus charge. The H plus will attach itself to the alkene, doubly bonded carbon, such that a more stable plus charge or a carbocation is formed during the reaction. Out of the two possible carbocation which can form during the reaction, the more you are going to choose a pathway which lead to the more stable. And this is 1 degree carbocation. The carbocation stability is, you can see, 1 degree carbocation. Okay, it is less stable. This is a secondary carbocation, 2 degree, because it is connected to 2 carbon. and this is a tertiary carbocation. And they also give their electrons, the CH, by hyperconjugation, and these alkyl groups also push their electrons slightly towards the carbocation, that make carbocation more stable. Clear?
Yes, sir.
Right, so H plus is going to attach itself such that a more stable carbocation is formed, and that is the governing factor for Markovnikov addition. And the stability of carbocations are 3 degree, 2 degree, 1 degree, and CH3. Okay, you need to check both